Okay, welcome back, everybody. So this is the very last lecture of the course. And some great advice I got in graduate school about giving talks was one way to give a talk, a solid talk, is to first tell the audience what you're gonna tell them, then tell them that thing, and then end by telling the audience what you've told them. So today I am going to give a very similar lecture to the first one that I gave. And I'm going to summarize the trajectory of this course and what we've learned and how all the pieces fit together on kind of a bird's eye view here. So here we go. So this was a course called Numerical Algebraic Geometry. Algebraic geometry is the study of polynomial systems and their solution sets. And so this story begins in the simplest setting for algebraic geometry, which is univariate polynomials. Over the complex numbers. The fundamental theorem of algebra tells us that univariate polynomials have degree many roots counted with multiplicity, but it does not give us any prescription on how to find those roots. For linear univariate polynomials, we know how to do this super well. Even for quadratic univariate polynomials, we're pretty happy. And one can do it for generic cubic and quartic polynomials. There are formulas for the roots of cubic and quartic univariate polynomials, where you can write the roots as field operations and roots, like nth roots of the coefficients of the polynomial that you're given. If you study Galois theory, you learn that this is no longer going to be possible for degree 5 polynomials or higher in general. Indeed, there are some degree 5 polynomials that you can solve this way, but not all of them. And so we're left with the question of what are we to do, especially if we're dealing with something in applications where we really want to get our hands on some like number, which is a root. And the answer is, at least from one point of view, is find numerical approximations. So floating point numbers are very, very, very close to the roots. Of course, the floating point number will never, in general, exactly be one of the roots, because a floating point number at the end of the day is a rational number. But we'll get something really, really close. So this will make people in applications happy, because if you're correct up to the, say 20th decimal point or something, then that's good enough to use that number in calculations and construction of bridges and things like this, and machines and robots. But of course, it's mathematically technically incorrect in some rigorous way. If I plug in that floating point number as a rational number into my polynomial, almost certainly I won't get 0 identically. I'll just get some very, very small residual. But nonetheless, we ignore the technicalities for the moment. Those come back at the end of the day in the certification section. And we ask, well, how would one even get these numerical approximations? And we go back to our experience as younger mathematicians in calculus, and perhaps we've learned about this Newton's method, which says that if you have a number which is near a root of a univariate polynomial, you can do something to it, and you can get nearer to a root of a univariate polynomial. Okay, and so this allowed us to take points that are really near roots and get them even closer. And that was great. And that gives you one way to kind of, if you'd like, stochastically try to find all the roots to a polynomial. Just take a bunch of random start points and hit it with Newton's method a billion times, and eventually you'll stop finding points, and maybe those are all your solutions, or maybe you just stop when you find degree many points converging. But that is not the approach we Rather, we take the approach of so-called homotopy continuation. Says that you got this f of x equals 0. It's hard. But you make something easy, which looks just like. And the easy thing is a univariate polynomial of the same degree whose roots you can just write down. Or at least write down numerical approximations for really well. And the choice is x to the d minus 1, where you have d distinct solutions for all the d roots of unity. So this is very easy to solve. And then the way to connect them is via this convex combination or this homotopy, so that at t equals 1, this h evaluates to g, and at t equals 0, this h evaluates to f. What this does is this sketches out little paths that you might hope to follow in some way. And the way you would follow it is via standard predictor corrector method, where you take one of your start solutions, which you know very, very well. You guess where that path goes after an itty bitty time step of, say, like epsilon. So now I'm at like 1 minus epsilon. And then since these paths are continuous, if I go an itty bitty distance in t, I'll move an itty bitty distance in my solution space. And that means I'm still close to some root, which means I can still use Newton's method and get even closer. So I predict under the faith that I haven't moved very far. And then I correct again under my hope that I haven't moved very far from a root. And then I repeat this process and try to march from the start solutions all the way to the target solutions. The problem happens in the fact that in order to use Newton's method or a more advanced predictor method like Euler's method, which uses some tangential information, I am going to need to make sure that the derivative of my polynomial at my root is not 0. Okay, and that's an issue because if I just try to use this way to connect f and g out of the box, it's totally possible that I have path crossings. And those path crossings have the feature that the derivative of the univariate polynomial system over that t value does have a root with multiplicity, or in other words, the derivative is 0. And so I won't be able to use Newton's method or Euler's method out of the box. So I'm concerned about these multiple roots that occur. And we learned that the way to fix this is to just throw some random complex number into this equation. So now at t equals 1, instead of being g, I'm some number times g, which has the same roots. So geometrically, it doesn't change anything. But what will happen is it'll all but guarantee, so with probability 1, that no such path crossings occur. Okay. And this is called the so-called gamma trick. Great, and so now it looks like our method's working. We have start systems, we can march along using numerical predictor corrector methods. We're guaranteed that along the way, our derivative is never 0, but there's one thing we can't guarantee, and that's what happens at the end. Right? Somebody could always be trying to solve a polynomial system with multiple roots, and so we're not going to have any control over what happens at the very, very end. And so indeed, if there are points with multiple multiplicity, then we're going to have a hard time approaching them numerically. And so we need some other way to find these points with multiplicity. And so we had a short discussion about so-called endgames, specifically the Cauchy endgame, which uses the Cauchy integral formula to approximate this root with multiplicity without ever having to get too near that root. Okay. Great. So after the univariate homotopy continuation chapter, we knew that we could solve univariate polynomials for their roots. And we can even understand their multiplicity because the multiplicity of the roots of our univariate polynomial equals the number of paths which approach that point. So we're really in good shape theoretically about solving univariate polynomials. And the next step was to beef it up to multivariate polynomials. First adjustment we have to make is that we have to have square systems. So as many equations as variables. But then still, we cook up a start system. We compute this homotopy with the gamma trick. And we get some solutions that are easy to find for the start system. And we try to use exactly the same methods we had before to find the solutions to the target system. What do we need? We need a multivariate notion of Newton's method. That exists. A multivariate notion of Euler's method. That exists. And then pretty much everything else follows from the univariate setting, with the exception that worse things can happen at the end. So in the univariate case, all we had to worry about was multiplicity. But in the multivariate case, we're often in a situation where we have some path that flies off to infinity, or in a situation where our path ends up not at an isolated solution, but as ends up landing on a positive dimensional solution component to this polynomial system. Okay, so there need to be measures put in place to handle this. Infinity, we ignored the concept of projective space in this course, and all I said was that you can set some tolerance so that if the size of a solution gets larger than that tolerance, you declare that's going off to infinity. That works amongst friends. We commented that when you land on a positive dimensional component, a feature of that is that the Jacobian is not invertible there, which is also what happens when you have a solution with multiplicity. And so there's this issue of not being able to distinguish between solutions with multiplicity versus solutions on positive dimensional components. And this was also something that we bypassed in this course and chose to focus on finding the isolated regular solutions of the multivariate polynomial system using this method. That was chapter 2. And after chapter 2, we're now promised that we have reliable numerical methods for finding the regular isolated solutions to square polynomial systems. In chapter 3, about parameter homotopies, placed the last 2 chapters into a common context. So in homotopy continuation, the first 2 chapters, we are very isolated. We have this one polynomial system we want to solve, but we have this method of cooking up another one and then deforming it to the one we want. But still, our focus is really just on this one polynomial system we want to solve. In a parameter homotopy, you think about that one polynomial you want to solve in the context of a family of polynomial systems. And then you understand that our old algorithms for choosing a start system and degenerating the solutions to our target system is really just a path in that family, right? So I have the polynomial system I want to solve. I put it in the family of all polynomial systems with the same degree sequence. I look at the Bezout start system. That's another polynomial system in my family that's very easy to solve. And then this straight line homotopy, this homotopy is really describing a path from that member of the family to the member of the family that I want to solve. And so I can think about both of these algorithms previously as really just moving solutions around with respect to some family of polynomial systems. So that is the point of view of a parameter. There we have some square polynomial system, which depends on some parameters, some solutions, so some variables, such that if I choose a point in the parameter space, I can compute the solutions to it. And if this point is just randomly chosen, then the parameter continuation theorem tells me that there exists some well-defined number d, which will count the number of regular solutions. And from this setup, we got our hands on a bunch of definitions. So one being the exceptional set. So this delta. This is the parameters that give funny behavior upstairs in the solution space. And you can even cast this whole gamma trick in the context of exceptional sets, is like the gamma is just choosing a different path in the parameter space from the start system to the target system at random. And since the parameter space is one-dimensional and the exceptional set is a complex zero-dimensional, a random real path will avoid the exceptional set, which is what we were worried about in the first place with path crossing. Okay, so yeah, big thing here was the parameter continuation theorem. And in some sense, we could have started the course from this point of view and then thought about homotopy continuation, the univariate and multivariate setting directly in terms of these families. But that's often not how it's presented. It's often not how homotopy continuation is has been understood and has like historically come about. And so I wanted to do it in this more direct way. Like I just have a polynomial system, I want to solve it. How do I do that? Okay, now chapter 3, what's really going on here? It's a parameter. Okay, what was next? Okay, so there was a bit of a discussion about different families. So if somebody hands you a polynomial system, which family should you put it in? There's always the choice of this total degree family, which is the Brysiewicz system as like a very nice choice of a start system. But then there's also this polyhedral or sparse family. And in that family, you're afforded a different upper bound on the number of regular solutions called BKK bound. So we talked about that a little bit. And then we mentioned, but did not go into the polyhedral homotopy. So there exists a way to cook up essentially a start system to a polyhedral family. Yeah, and that is the default way to solve things in homotopy continuation. We then started discussing monodromy, which exists in the earlier numerical algebraic geometry algorithms, but has really gotten a lot of traction, I would say, over the last 10 to 20 years. There's a lot of cool algorithms. You can do a numerical algebraic geometry based on the concept of monodromy. And again, we end up drawing a very similar picture to the one here in this parameter homotopy. We think about having some parameter space still and some variety which tracks the incidence of solutions along with their parameters. And we think about the projection onto the parameter space as a branched covering. In the topological sense, which means it's essentially a covering space except for over the exception set. And as soon as you have a covering space, you're allowed to think about monodrome. So if I have some points down here, and I have some number of solutions to the corresponding polynomial system, I can use homotopy continuation to kind of run around this parameter space, and maybe I take a loop in my parameter space, and that means that these points will travel around, and then they'll come back, but they may have swapped positions. And this swapping phenomenon is called monodromy. we define the monodromy group to be all the possible permutations that could occur. Okay. So talk about monodromy, loops. We talked about the fundamental group a little bit because there's a well-defined map from the fundamental group of the parameter space minus the exceptional set up to the so-called monodromy group. Subgroup of some symmetric group. And we discussed a little bit about the dictionary between properties, group theoretic properties of this monodromy group and geometric properties of this branch cover. So for example, if X is irreducible, which is really what it means to be a branch cover, then G pi is going to be transitive. If instead X is a union of a bunch of reducible components, a bunch of irreducible components, each of which, when restricted pi to that component is a branch cover, then you're going to get several orbits of this group, of this permutation group. And then we talked about two transitivity a little bit. We talked about imprimitivity and how that has to do with decompositions of this branch cover. And then we also talked about monodromy solving. So unlike the methods in the first two chapters of this course, which solve a polynomial system by constructing a suitable start system that's easy to solve and then performing a homotopy, monodromy solving solves a polynomial system in a fundamentally different way. What it does is it finds a single solution in a single fiber of this branch cover and applies monodromy loops to populate the rest of the fiber. Okay. So the big difference between monodromy solving versus homotopy continuation. Homotopy continuation requires tracking d many paths, where d is the generic number of solutions in the family that you've put your polynomial system into, right? So if you put it into this total degree family and you want to use the Bezier start system, then you're going to have like the product of the degrees of the FIs, many paths that you have to solve. Or if you put it in the polyhedral system, you'll have the mixed volume of the Newton polytopes of each of the FIs. Many paths you need to follow. And both of these are upper bounds for the number of solutions to your system, thanks to the parameter continuation theorem. However, they may be drastic upper bounds. The true number of solutions may be nowhere close. So you may have a Bezier number, which is in the millions, and a BKK number, which is in the millions, but you only have 5 solutions. All of the other paths are going to be wasted computational time. Monodromy solving is distinct from a computational point of view because it doesn't care about this family's bound so much. It's really an output sensitive algorithm. And we showed that on general, you expect to need around like log of the true number of solutions, many loops. Yeah. To do monodromy solving. No, it's linear. Okay, so I'm not remembering this off the top of my head. There was a harmonic number involved, so go back to the lecture. But it was really like the difficulty of solving via monodromy was a function of the true number of solutions, not the bound that you're able to see at the outset. So that was monodromy. And we needed to do monodromy before we did the next section. Because the next section, so at this point, we have monodromy, we have homotopy continuation, we have parameter homotopies, we have all of the necessary background to really start talking about numerical algebraic geometry. So homotopy continuation methods have existed for a long time. Numerical algebraic geometry, I think, really starts picking up when you are able to handle not just zero-dimensional varieties, i.e. solutions to, the finitely many solutions to a polynomial system, but you can actually understand varieties, which are positive dimensional, this way. And the way you do that is via witness sets. You essentially do the tried and true move of, oh, hey, this is a really hard thing to do. I don't know how to describe infinitely many solutions, so I don't know how to describe this positive dimensional variety. But I do know how to find zero-dimensional varieties, so let's just make this into a zero-dimensional variety by intersecting with an appropriate number of hyperpoints. Linear. Okay. So in this case, it would be, on the blackboard, it would be intersecting with two hyperplanes, i.e. intersecting the surface with a line, and then computing the isolated solutions in this intersection. That's all well and good when your variety is irreducible of some dimension. Well, what happens if you have multiple components? So you have the same, right? Well, what do you do then? I want to be able to represent one of these components using numerical algebraic geometry, but I have a bunch. So it turns out monodromy is exactly the way to split up your intersection points, because as you move the line around, you're doing a loop in the parameter space of all lines. And none of the points on one component can move to another as you move that line. So in other words, the orbits of monodromy have to belong to a single component. And then we have a theorem that says that indeed, if you do restrict this problem to a single component, your monodromy is the full symmetric. So the orbits of monodromy of this witness problem, i.e. the problem of finding these isolated zeros when you stab with a linear space, these orbits exactly correspond to the components of your variety, in the case that you're equidimensional. Now, if I have some other components, which are different dimensions, then I have to use different dimensional linear spaces, and being able to find witness sets for all of the components is the big algorithm in numerical algebraic geometry called a numerical irreducible decomposition. So this gobbles up some polynomial system and spits out a bunch of witness sets, one for each component. And staying in theme with the course, we ignored components that have some multiplicity. Okay. As soon as you have witness sets, you can do a whole bunch of stuff that you'd like to do. You can try to find equations using numerical interpolation. You can check membership of points. You can sample generic points. You can check containment of irreducible varieties. You can compute witness sets for projections very easily. And so this is really a great way to represent varieties, because lots of the things you'd like to do, you can do fairly easily when you have a witness set, and you're equipped with the ability to move those witness points around via homotopy continuation. Okay. So hopefully that chapter gave you a flavor of what kinds of things numerical algebraic geometry can compute about your favorite variety, even if it's not zero-dimensional. And then the final very short chapter here we just discussed today. And last lecture was certification. Harks back to the earlier concern in the first chapter about finding a numerical approximation for a root of a univariate polynomial system. So we've come full circle. We've done a monodromy loop in the course, and we get to answer the concern about what does it mean to find a numerical approximation of a root of a univariate polynomial system. Amongst friends, you've pretty much found the root, but amongst adversaries, maybe it doesn't mean much. Certification kind of handles that by saying that you can't actually prove that true roots are distinct, unique in a bunch of intervals. So find your 10 isolated solutions to a polynomial degree 10 as numerical approximations. You can put little intervals around those 10 solutions, and you can prove that there is a unique solution in each one of those intervals. So that's the flavor of things you can prove. At least right now with the available software, numerical algebraic geometry. Yeah, and so that was course. So thank you for coming. I hope you've learned a bunch. I hope you learned how to look at polynomial systems and their solution sets in a new way. I've enjoyed very much having you all in class. If you're online, thanks for watching online, and feel free to shoot me an email with any questions you have about this course. So thank you very much.